Hello and welcome to the second part of Lesson 7. In the previous part of this lesson, we saw how to model a two-dimensional, steady-state heat transfer problem. We followed our workflow to determine that it was a two-dimensional problem, and then used Mathematica to calculate a numerical solution to the partial differential equation that resulted. This time, we're going to take this one step further and look at how one might solve a two-dimensional transient problem. As we do this, we're going to uncover a valuable source of data that can be used to both validate numerical solutions or give us directly usable information for a given problem. But before we get into that, let's look at our workflow again. So here on the whiteboard is the workflow that you're by now very familiar with. So I'll just run through it quickly this time since we've already talked about this at length. The nub of this really is to sit down and think about the problem, then identify the key mechanisms of heat transfer, identify whether it's 1D or 2D, figure out what coordinate system best describes the geometry that we're looking at, and typically it's going to be Cartesian for a slab or cylindrical polar for an extruded rod or a fibre, and then simplify the energy equation, look at it in vector form to start with to eliminate the physics that we're not bothered about, and then drop it into the coordinate system of choice. And we're going to be left with probably either a relatively simple partial differential equation that we solve numerically, or even an even simpler ordinary differential equation that we can solve analytically. So we're going to use that workflow again. We're going to go through exactly the same steps, but this time we're going to look at a time-dependent problem. And so in order to make the problem time-dependent, I'm going to change the physical scenario a bit. Rather than looking at extrusion and extrude cooling, I'm going to look at injection moulding. So the mental model that I've got of this process is that I've got a mould, I'm squeezing molten polymer into that mould, and I'm assuming that the mould temperature is roughly the same as the polymer melt temperature to start with, such that we can actually easily get the polymer into the mould. Then what I'm doing is cooling the mould, such that the polymer inside the mould cools. Fine. So I'm going to abstract and idealize that concept somewhat, such that I can really underscore the point that I want to make in this part of this lesson. So we're going to end up by making actually quite an unfeasibly large injection molded product. In reality, you wouldn't do it like this, but it does give us a very good way of emphasizing this heat transfer problem that I'm trying to create here. So step one, let's draw a diagram. There on the whiteboard is a schematic of my injection mould. It's a rather simple one. So I've just got my top and bottom mould walls in grey there, and the molten polymer in orange in between. I can change the temperature of my mould walls, and whilst the polymer is cooling, I'm going to say they're at a cold temperature Tc. So let's zoom in on this molten polymer a bit. There in my little control volume in red, I've included my mould walls, upper and lower, and I've included the polymer in the middle, and I'm thinking about how heat can be transferred between the mould and the polymer. Well, nothing's moving, is it? There's no extradate motion, there's no advection, so that's one piece of physics that does not apply to this problem. We're assuming that we're cooling the material by imposing a change in temperature at the upper surface and at the lower surface, and that there's no contact resistance between the two. So there's no convection going on, but if we were to think about this, we're assuming that there's perfect heat transfer at the surfaces, kind of corresponding to a convection heat transfer coefficient of infinity. Okay? So the only thing from a heat transfer mechanism point of view that dominates heat conduction in the bulk of the polymer is thermal conduction. So we have a purely conduction-based problem of a molten polymer in a mould where we're assuming perfect heat transfer from the polymer to the mould, where we can instantaneously change the mould temperature. Okay, so imagine that what we've got is a mould with cooling channels built into it. We've got the mould nice and hot to accept the molten polymer coming in, and then we flood those channels with coolant, and we achieve a near step change in mould temperature. It doesn't really work that quickly, but for the purposes of this example, we're going to assume that it does. Let's just build on our mental model a little bit here. If we're assuming that we've got this perfect step change in temperature, what do I expect to happen to my product? Well, If my mould completely surrounds the product, I might expect a 2D temperature field because heat conduction is the only thing that's going on, and I know that takes some time, and I know I've got a poor thermal conductivity material. So I might expect a 2D temperature field that decays actually over a very long time. The thicker the product is. If I've got a very thick product, it might even take hours to cool. All right, so that's my mental model so far. Let's move to step 2. Let's formally decide whether this is a one-dimensional or two-dimensional problem, and we're going to do our BO number analysis. And remember what we said last time, we're assuming that there's perfect heat transfer from the surfaces of the polymer into the mould, and so there's no resistance to heat transfer there as we would find in a convective scenario. So that infers that if we were to frame a convection heat transfer coefficient for this problem, it would be infinity. There's perfect heat transfer. And so we can do that. The other thing we need to do to establish our BO number analysis is make some assumptions about the thickness of material and actually what the material is. So let's assume we've got polypropylene again, just for consistency with the previous examples. You're familiar with the physical properties by now. And let's assume we've got an extremely big injection moulding problem here. Our moulded slab thickness is 100 millimeters. It's rather large. That's a rather big mould. I'm not quite sure what you'd use such a big mould for, but it's big. So we expect, thinking about this, for the cooling to take a very long time. Now, if you've got 100 millimeters of poorly thermal conducting material, it isn't going to be a fast cooling problem. Okay, so the BO number analysis allows us to figure out whether we've got a 1D or a 2D temperature field. There's my BO number. Remember what we said about that perfect heat transfer on the boundary, corresponding to an infinite heat transfer coefficient. It's a 2D gradient. Okay, fine. So we need to solve our temperature field in X and in Y, but also in time as well, because we're looking at the time-dependent cooling. So we're going to do this numerically. We could again do this analytically, separation of variables, but we're not going to. So let's move to step 3. Let's think about our coordinate system, and let's think about simplifying the vector form of the energy transport equation. I've said we've got a slab of material. I'm going to choose a coordinate system that is Cartesian. I'm going to place my coordinate axes in the center of that slab because I'm assuming that my die wall temperatures or my mould wall temperatures are going to be the same, either instantaneously the same hot temperature or instantaneously the same cold temperature. I'm going to focus my analysis now on the bulk of the material sitting within the mould. So there on the whiteboard is the energy transport equation. And again, let's go through this term by term so we understand exactly what physics we're including in the problem. I'm going to assume that there are no heat sources. Now, if we were actually driving a phase change here, that wouldn't strictly be true. We'd need to take into account the latent heats. I'm not going to for the purposes of this problem, but if we were to include it, that's where it would appear. And we'd have to put in some logic around when that became a heat source and when it did not become a heat source. So we'd have to figure out how to work out whether the material in our little control volume is solidified or not. I'm not going to go into that complicating factor now. I'm going to neglect radiative heat transfer. I'm going to neglect convective heat transfer. Those two modes don't exist, particularly within the bulk. I do, however, have conductive heat transfer, and heat conduction can happen in both of my coordinate directions, both in X and in Y, because of the two-dimensional nature of the cooling problem. If we look on the right-hand side of the equation, I do now actually have a time-dependent problem. So that partial derivative of temperature with respect to time is now non-zero, and is an integral part of the differential equation that we're going to be solving. That final term, the term for advection, well, we've got a static system. There's no product velocity, and so therefore the advective term is set to 0. So I've simplified the vector form of my transport equation. Let's drop it into the coordinate system that we've chosen, the Cartesian coordinate system. And we can see that we're simply left with a description of heat transfer by conduction on the left-hand side versus the heat loss that we expect as a function of time on the left-hand side. So those are the two key things that we're going to be solving for. So we've got a partial differential equation in 3 variables, x, y, and t. All right, so let's think about boundary conditions as our final step, step 4. I'm going to put my simplified energy equation there on the board. And now let's think what's happening in terms of boundaries. So I'm going to identify boundary 1 as the top surface, boundary 2 as the right-hand edge, boundary 3 as the lower surface, boundary 4 as the left-hand edge. The assumption that I'm going to make is that boundaries 2 and 4 also have some cooling attached to them, and that the cooling that boundaries 2 and 4 experience is going to be same as boundaries 1 and 3. So at the start of my calculation, at time equals 0, I'm going to suddenly impose a boundary condition at these edges that is a specified temperature. T equals Tc for T is greater than or equal to 0. Okay. If we've got a time-dependent problem, we also need to know what the initial temperature of that polymer melt is. We might be fine specifying, okay, we've got our nice cold boundary temperature all around the boundary, but what are we cooling the polymer down from in terms of temperature? So the other thing I'm going to specify is an initial condition. And that initial condition is that at time equals 0, before I change that dye or mold temperature, my polymer is uniformly at my melt temperature Tm. So I've got my boundary condition and I've got my initial condition. All right, so now we've established the equation. Now we've established its boundary and initial conditions, we can set it up and solve it. And we're going to again do this in Mathematica. So in terms of the Mathematica script, the first thing we do, as per last time, is set the physical parameters of the problem. I've set my thermal conductivity, the length and thickness of my product, the melt temperature, the mold cooling temperature, the density and the specific heat capacity. And I've assumed that my moulded product is 20 centimeters in length and 10 centimeters in thickness. As before, the next thing I do is specify the geometry on which the equations are going to be solved. And remember, the rectangle definition in Mathematica takes just 2 corners, the bottom left corner and the top right corner. And I've assumed again that the bottom left corner is at the origin of my geometric domain and the top left corner is at the length and the breadth of my geometric domain. So same geometry as last time. All right, so let's now think about defining the equation that we're solving. Now note we've written this a little bit differently to last time because we have no convection boundary conditions, and so in Mathematica we would incorporate those convection boundary conditions into the transport equation itself, but we have no convection going on here, so we can simply just write the 2 terms of the equation equal to 0. The terms in blue are the time-dependent terms, and let's just unpick that slightly in Mathematica script. We've got rho times Cp times capital D, which remember we said was the derivative operator, of the parameter that we're taking the derivative of, temperature, now as a function of x and y and t, because it changes with 3 parameters, and we're taking the derivative of temperature with respect to t. Okay, so that first statement in blue is simply the statement, as I've written on the board, of rho Cp partial dt by partial dt. The second set of terms are the conduction terms, and it's the same second derivative term that we looked at last time. Big D being the differential operator again, t being now a function of x, y, and time, and the 2 x's, comma separated, establishing that we're taking the derivative of t with respect to x twice. So it's just partial d temperature by partial dx squared. And then the same for the y direction. So that is my partial differential equation defined. I now need to define my boundary conditions. Constant temperature boundary conditions, as before, get put into a different statement. And I'm using the Dirichlet conditions operator here. A Dirichlet condition is just saying I'm specifying the value of the parameter rather than the value of the derivative of the parameter, which would be a Neumann condition. So here I've got 4 boundaries, and I've color-coded each of the Dirichlet condition statements according to whether we're looking at boundary 1, boundary 2, boundary 3, boundary 4. Let's take as an example boundary 1 in blue. And boundary 1, we can see we've got the Dirichlet condition of the parameter temperature T as a function of x, y and T, all equaling Tc, my cold mould temperature. Then I've got the geometric part of the boundary which that ascribes to. In this case, boundary 1 is at y equals b, it's the top surface, at all length, x equals 0 to L. And we can see for the sides, we are specifying, for example, for boundary 2, x being at length L, and then changing y from 0 to b. And so we've got those 4 boundaries implemented by Dirichlet boundary conditions as a separate statement in its own right. All right, now we obviously need something else here, don't we? We need an initial condition. So let's think about the initial condition. We're specifying this at time equals 0. So that's where the 0 comes in that set of square brackets. So uniformly in x and y, but at 0 time, we're saying that t equals tm. And that's what we said in the previous bit on the whiteboard, where we said, look, the temperature initially is the same everywhere. All right, so that's the equation and the boundary conditions and the initial condition all set. Let's solve it. We're using ND solve value again. The first set of parameters, that list within curly brackets there, consists of the equation that we're solving, the boundary conditions that ascribe to it, and the initial condition that we've stated. What are we solving for? We're solving for capital T, temperature. Fine. What are we solving with respect to? Well, we're solving over a time frame now. And I'm going to time step for 20,000 seconds. So time here is going to be in seconds. What geometric region is this going to be solved on? Well, it's the rectangle that represents our injection moulded slab. So x and y are linked to or are part of that computational domain that we've already stated. Finally, we need to figure out what the calculations actually come up with. So we're going to, in this case, plot just a temperature profile. I'm not going to bother with a contour plot, but at a certain time, I'm going to plot the temperature through the section of the material, right through the middle of the material. So I'm going to plot a line graph halfway along the mould, right the way through the thickness at an ascribed time of 7,700 seconds. All right, so let's see what that looks like. So 7,700 seconds, that's just over 2 hours. And I can see that, well, wow, the centre of this mould is pretty hot. So this graph is temperature as a function of thickness. I put a little diagram on the board next to the plot with a dotted line to show you where we're looking at the thickness. It's from top to bottom in the middle. And there's a long way to go in terms of cooling. So this matches my mental model, doesn't it? Because a poor thermal conductivity material that's very thick is going to take a long time to cool. It's taking a long time to cool. And I would expect a symmetric temperature profile because the top and bottom temperatures of the mould are the same cold temperature. And that is precisely what I've got. All right, fine. Can we trust this answer? Same old question. We need to validate this. So how can we validate it? We somehow need some analytical data or some established data that we can compare this to. What we can do is look in the literature and use something called a Heisler chart. Now I'm going to be talking about Heisler charts in more detail in the next part of this lesson, but they are non-dimensional representations of the solution by separation of variables of the heat transport equation in various geometries. And so they're analytical in origin. Very, very useful. They're presented in a non-dimensional manner, so they can be adapted to a number of different practical scenarios. So what I'm going to do is I'm going to extract non-dimensional data from a Heisler chart. I'll give you an example of a Heisler chart in a minute. And then I'm going to non-dimensionalize this temperature profile such that I can compare the two data together. So let's look at our Heisler chart in brief. As I said, I'm going to be talking in far more detail about these in the next part of this lesson, so don't panic at the moment if you haven't seen these before. We're going to go over them in some depth. But what they are non-dimensional temperature plotted as a function of non-dimensional distance at various non-dimensional times. So, in order to figure out what non-dimensional time we're at, we need to know our parameter alpha. Alpha, in this context, is our thermal diffusivity, which is K over rho Cp. And for the physical properties of the polypropylene and the geometry of the slab that we're dealing with, we get alpha is about 0.2. So I've highlighted the line on the Heisler chart that represents the non-dimensional temperature profile that we should be getting with the product of the numerical solution. Please note that when we're looking at the geometry B here, B is the half thickness, not the full thickness of the slab. All right, so what am I actually plotting? T minus T0 over T1 minus T0. Converting those parameters to the parameters of the problem, T is a temperature that I'm interested in at the time now. T0 is the initial condition, so that's my melt temperature, Tm. T1 is a condition of the boundary, and that's Tc for this particular problem. So the y-axis can be rewritten T minus Tm over Tc minus Tm for our particular problem. And the x-axis is simply x over b. This is the fractional thickness away from the middle of the slab. If x equals 0, or if that parameter equals 0, then our half thickness is 0, we're in the centre. And then if it's 1, we're at the edge. So we're looking from the middle to the edge for our temperature profile. And so it's taking into account the symmetry of the problem. All right, so let's extract the data from that green line, and let's non-dimensionalize the data from our numerical solution and plot them together, and this is what we find. I'm happy with this because my numerical solution, which is a blue dashed line, nicely coincides with the Heisler chart data, which is the series of red stars. So the Heisler data and the numerical solution are the same. That makes me happy because I now know that I can trust my numerical solution. So Heisler charts are very useful. We're going to explore them in the next part of this lesson. So let's recap a few key points. Again, we've gone through our heat transfer solution workflow. We've used it this time to examine a two-dimensional transient heat transfer problem. We simplified our transient problem where all the boundaries of the hot product are assumed to take at a step change a new temperature. So we did that such that we can make a direct analogy to a Heisler chart. Now that we've established our numerics are correct, we can change those temperature boundary conditions and maybe represent a more realistic problem. So what we did as a first step, as always, was validate our numerical solution. And we're going to look at the tool that we use to validate that solution in more detail next.